Hi, welcome to our group presentation based on fetal and placental weight/volume data that's based off of the medical text Human Body Composition by G. Forbes. Molly examined the graph that was given in this data, and she found that the fetus growth in grams per day is on the y-axis along with the placenta growth that's also in grams per day. The x-axis shows the growth starting at 15 weeks into pregnancy until 25 weeks after pregnancy. The data is in the first derivative form because it is not given in an exact period of time. Rather, it's just the grams over weeks of the specific data. Therefore, it's the derivative function.
Problem 2 for our project was to use grid paper and a ruler to estimate the coordinates of data points for both the fetus and the placenta, and to make units of measurement consistent and make two figures based on the fetus and placental growth data. So here is the fetus growth rate in terms of days. We converted weeks into days to give it a more consistent reading of its growth, and based on the scatter plot you can see that it kind of dips down a little bit and then rises back up, but these are all very minimal changes. But you can, if we use the line of best fit, you can see where the inflection point is if you wanted to. So moving on to the placental growth rate. So comparing these two, the placental growth rate took a lot longer to actually start growing, and comparing these two, we can see that the fetus grew faster or took less time to grow than the placenta, but also dipped, whereas the placenta didn't really dip as much as it just stayed consistent. Moving on to problem number 3. It was to fit a polynomial of 1 degree to each set and report the fitted equations and r-squared values. So basically, this is what happened when we plugged it into Desmos. So clearly there is a line of best fit through the scatter plot, and it's kind of dips and inclines throughout. But I would say that this fits well because based on our equation and plugging in numbers, we were able to find data that was similar to the data that we were getting in the problems beforehand.
For number 4, the fitting for the polynomial of degree 4 is a lot better of a fit because unlike question 3, these lines go through all of the points for both the placenta and the fetus. This is because it's a polynomial and not a straight line. It gives a more accurate understanding of the pattern given by the points, especially because we had to add at least 10 decimal digits after the numbers. In this picture specifically, you can see the equation that we used to find the fetus in a polynomial of degree 4. This image shows the numbers and the equation that we used for the placenta, and the blue line represents the fetus and the purple line represents the placenta. Problem 5, we had to find the second derivative, and we found the first derivative from problem 4 from the equation that we used and the numbers that we got from the Desmos chart. Therefore, in this image, you can see the first and the second derivative of the fetus. Here you can see the first derivative line, which is black, and the second derivative line, which is in red. And to clarify, the y-axis, again for the fetus, is measured in grams per day, and the x-axis represents the days. We went through the same process for the placenta, where we found the first derivative from problem 4 in the same equation. And then from the first derivative, we calculated the second derivative. Here in Desmos, you can see the first and the second derivative for the placenta. The first derivative is the green line, and the second derivative is the black line. In comparing these two with their inflection points, you can see that the fetus inflection point comes a little bit after the placenta inflection point. Therefore, for problem 6, we concluded that the inflection points for the placenta weight and the fetal weight seem to occur around the same week. However, the placenta inflection point comes before the fetal inflection point. In problem 7, here you can see the fetal and the placental polynomial equations. We got these equations from the equation that we put in for question 3. That gave us a line of best fit for these points. And after plugging in this equation into Desmos, we were able to derive the numbers in order to figure out this polynomial equation. We plug these numbers back into Desmos, and here you can see the line for the fetus and then the line for the placenta.
So now moving on to problem number 8 and figure 7. So for question 8, we had to enter the data points into an Excel sheet where t equals 0, and explain the physical interpretation of this value. So basically, we see a line that represents the growth of the placenta and or the fetus, and with these two equations here, it creates both of these lines. We have one with a scatter plot with a line of best fit, which is this equation right here, and then we have this purple line that is represented by this equation here. And when we take the second derivative of equations or polynomials like this, it can give us inflection points. And when t equals 0, we can see that the placental volume is also at 0, because that's what shows here in the graph. And basically what that means is that when there was at the beginning of this, the placental's volume was nothing. So problem number 9 and 10 are basically asked to compare the inflection points of the data from the placental weight from the article and the prompt that we were given. And so basically, to find inflection points, like I said earlier, you just have to find the second derivative of the equation that you're using, and then use the second derivative should give you the inflection points. So if we want to compare the placental volume and placental weight, we must look at the data in the graphs to find out where the inflection points lie. If we can find these points by looking at the graphs and where the points changes direction, we can see where the volume and the weight is based on taking the second derivative of the equations. If I think that these numbers are a little bit skewed and inconsistent, because the placental volume that I found was at week 4, where the volume was at negative 47, and for the weight of the placenta, I estimated from the chart and came up with the inflection point that was on the coordinates 27, 24. So basically this means that week 27, the weight of the placenta was approximately 24 grams. And I don't think you could really compare these two, because for the placental volume, there's a negative growth. And I don't really think that kind of makes sense, because how can something grow negative compared to the weeks before? On problem number 10, as we can see right here, is to make a medical conclusion about these the placental volumes, inflection points, and being in the same period as placental weight. So if I were to draw conclusions from these data charts and information, I would say that the placental volume does not match the same time period as the weight from the article, because they're both at different times in its lifespan. Like, obviously, if something's younger, it's going to be a lot smaller and have less growth compared to someone some placenta or fetus that's in its prime and growing the strongest. I trust the article data more than the chart that was given to us, because the data is very skewed when looking at both. And looking at the article, it seems to me that the information in there was more trustworthy than the changed numbers in the graph. Thank you.